Hello everyone, I am Carlos Lua from University of Siegen. Today I'm going to talk about the AI scheduling components developed by Siegen within the work package 4 of the FRACTAL project. The purpose of this video is to show the functionality of the components, so they can be utilized if needed by any of the partners within the FRACTAL project. First, I will give a short explanation of the objectives within the task. Then, I will provide a general view of the process to see how the components are connected with each other. Finally, I will explain each of the components, their purpose, and how to run them. Specifically, task for the two objective is to develop energy-efficient and dependable scheduling algorithms for a hierarchical time trigger fractal system. The aim of the AI scheduling components is to provide a temporal and a spatial resource allocation strategy for a single fractal node. The AI scheduling consists of four main components: the scenario generator, the scheduler algorithm, the machine learning model, and the reconstructor. The objective is that depending on the structure of an initial model formed by different tasks and messages, to provide a predicted schedule that contains the spatial and temporal allocations of the tasks. The first component is the scenario generator. It is in charge of creating all the synthetic data. A large number of different scenarios formed by an application and a platform model. The platform model, which indicates the topology of the system, can be adapted to any specific requirement. We can have a bus topology, a mesh, or also a different topology defined by the user. The application model will be different on each of the generated scenarios. We can also delimitate how random the application model should be by defining certain parameters like the maximum out and in degrees of a node or the size of the task and messages. So I'm going to show how to run the scenario generator component. We are using the Snap library, a Stanford Network Analysis Platform, to generate graphs for the application and platform models of each schedule. And that's why we need to have it here. First, we have to define some parameters for our initial model. For that, we can open the parameters.txt file. Here, we can modify the number of jobs or tasks we want in all the scenarios. Then we specify how many scenarios we want. In this case, we'll just generate 100. The next line indicates the topology of our system. We can select bus or mesh, or in case we want a particular topology, we can define it manually in the code. The next lines will define the number of switches and end systems we want to have depending on the topology we choose. So first we have to compile it if any modification is done inside the code. Right now, nothing was modified. The source-gen executable is generated, and we can run it by typing the next command. As we can see, all the scenarios are being generated. When the code finishes, we can go inside the graphs folder to check the topology is correct and also to take a look of the different application models that were generated. And you can see here is logical, it's another name for application model, and the physical is known also, the platform model is known also as physical model. If we take a look at the topology, we can see that as we define it, we have 3 switches and 2 end systems connected to each switch. In the case of the application models, we can see that we have 10 tasks on each of them, and yeah, all of them are different from each other. Inside the scenarios folder, we have the JSON files, 1 per scenario. And if we take a look to one of the files, we can see all the information of the scenario. So let's take a look at one of them. In the application model, we see the properties of each job, like the ID, the worst case execution time, deadlines, or limitations, stating in which end system are the tasks allowed to run. Of course, it's possible to add or modify these properties based on the application. If we scroll down, we have the messages, information like the ID of the messages, which job send the message, which job receive it, and the size of it. And finally, we have the information of the platform model that indicates the topology of the system and how are the nodes connected, and in case the node is a router of an end system. The second component is the scheduler algorithm. The scheduler algorithm will receive the data created by the scenario generator and will provide the best scheduling solution to each scenario. We chose the genetic algorithm as the scheduler component. Genetic algorithm is meteoristics that is based on the evolution theory via natural selection. In the GA, initially, there will be a certain number of individuals, called chromosomes, that constitute a population. Each chromosome is made of a combination of genes, and these genes represent the parameters or variables of any application we want to solve. In our case, a scheduling problem. On each iteration or generation, the chromosomes are modified by different processes, like crossover or mutation. A fitness function is applied to each chromosome to detect the ones with the highest fitness score, and those are chromosomes then continue to the next generation. The rest are eliminated. The idea is that at the end of a certain number of generations, we will have the best possible chromosome. Now we have to define the meaning of the genes in the chromosomes for our application. We divided the chromosome into 3 sections. The first section indicates the allocations of the tasks, meaning in which end system they will be executed. The next section is for the priorities. These priorities will define the order of the tasks. And finally, we have the routing section that chooses a route from the list of possible paths for a message to go from one end system to another. Each generation, the GA will reconstruct the schedule for each chromosome to determine the fitness function based on the make span, which is the time it takes until all jobs are processed. I'm going to show how to run the genetic algorithm component. All the files that we created in the scenario generator component are stored in the JSON folder. These are all the scheduling problems that the GA needs to solve. Normally, we have around 40,000 problems since we require lots of data for training. Solving all of them with the GA one at a time will take days, even weeks, depending on the complexity of the problem. Right now, we are using the university cluster to help us running the GA in parallel in a couple of hours. We are using 25 nodes of the cluster to run a total of 40,000 scheduling problems. Each node can execute 64 tasks at the same time. That's why we are dividing the files into 25 folders so they can run in parallel. You need to divide the files depending on the capacity of the system that you're planning to run it. The process of copying files, dividing them, and so on, it's already automated in a script file that I will show on later. So once the files are already separated into folders, we can execute one folder at a time. We can take a look at one of the script files. Here we are just defining the resources we will use, which in this case for each script file, we're using a CPU node that can execute 64 tasks at the same time. The script file is in charge of running the GA code with each scheduling problem inside the input folder. To run all the script files, we are running this run xarg script. So this will run automatically all the scheduling problems, no matter in how many parts we divided them. At the end, we'll have all the solutions in the results folder. Here I'm just printing 10 of them. And if we take a look of one of these files, we can see all the scheduling information. So let's open one of them. So we can see information like the position of the jobs, the end system in which each job is running, or also the start time. In this example, each scenario contains around 70 jobs. So if we scroll down, so at the end of these 70 jobs, we can see the make span. Below the make span, we can see the information of the messages, like the arrival time, the injection time, or also the route that the message took. The next component is the machine learning model. This component takes the files generated by both the scenario generator and the solutions from the scheduler. An intermediate step is needed in order to process the data, extract the information from the JSON files, and compute the features of each sample. For this component, we are using specific tools to help us with the data processing and the machine learning. Tools like skitlearn, TensorFlow, Keras, NumPy, and Pandas. All these in the Python environment. We chose artificial neural network as the machine learning model to predict the task priorities. The number of nodes in the input and output layers depend on the number of features and jobs that we have. We first need to extract features that capture the behavior of our scheduling problem, such as the number of jobs, number of messages sent and received by each job. Since we want to predict the job's priorities, we are comparing the priority of each job with the rest of them, having at the end a vector of binary values. This means that our model performs multi-level classification. I'm going to show how to run the machine learning model component. This component runs after the scenario generator and the genetic algorithm, since both components generate the necessary data to train the model. We created a script file that runs all the components in an automated way to save time. The script file takes care of the path in which you are running the components. In the case of the genetic algorithm, It makes the parallelization easier by splitting the files in batches. The first component, the scenario generator, is running in the step number 2. After the completion, we are running some commands that move the data, copy it, and prepare it for the genetic algorithm. All these steps already take care of the division of the data in parts, depending on the capacity of the system. And it's until step number 13 that we are running the script file running xargs. This script is the responsible of running the genetic algorithm for all the scheduling problems. Right after that, we are installing all the necessary packages that contain the machine learning tools. Finally, in the last step, we are running the machine learning model with this input line. After the data processing and the training process, the Python code will generate a file of the training model in H5 format. The file contains the layer structure and the weights of the artificial neural network. The last component is the reconstructor. This component takes the prediction of the machine learning model and creates the schedule. In the reconstruction process, we are not only building the complete schedule, but also we are making sure that all the conditions are met. And in case of a message collision, we have to deal with it. All this process is because we cannot rely 100% on machine learning, since one little mistake can damage the whole system. The reconstructor will give us the chosen schedule in a table, making it easier to extract the information.